get started. I see people are still filtering in, but I wanted to take the opportunity to welcome everyone. We've had a bit of a summer break. I hope you've all had a wonderful summer. Welcome to the September version of Pain Research Working Group. Today we have Dr. Michael Kashner presenting on causal modeling, fact, fantasy, or fake. So Dr. Michael Kashner is a graduate in mathematics from Northwestern University with doctorates in economics and medical care organization from the University of Michigan and law from Oklahoma City. He is a senior scientist in the Office of Academic Affiliations at VA and a professor of medicine at Loma Linda University School of Medicine. Since 2010, his focus has been developing causal predictive risk and outcomes models based on new tests for model classification that accounts for heterogeneity in outcomes and using administrative and survey data. I'm going to go ahead and stop so Dr. Kashner can go ahead and proceed with his presentation. As we mentioned, we'll be having a few questions at the end. So in about 5 till, I'll probably jump in and we'll select a few questions from the chat. So I'm going to turn it over to you, Dr. Kashner. Thank you for joining us today, and we're all really interested in hearing your
and thank you for having me. You can see my slide. It should be causal modeling, fact, fantasy, or fake, and then it has my name.
Yes.
So if you can see that, that'll be great. I have this on full screen, so and my slides are very space intensive, so it should be fairly clear. Let me say I have no interest in this commercial company below, or no conflicts of interest to report. All of the soft BAM analysis that we did was done by Stephen Henley at Martingale Research Corporation through his SBIR program funding. So all of the BAM calculations were done by him, and he's got really great software. He is a VA contractor also, by the way. Let me also say that I don't think any of you will be better clinicians as a result of this seminar, but I'm hoping to focus more on making better scientists and better science by using some advanced software that we've found to be quite useful. As an overview, I want to give you an overview of causal modeling, talk a little bit about two methods. The more traditional one is propensity scoring, and the one we're proposing is best approximating models. And we're going to look at performance specifically in terms of how they handle unobserved confounders and account for treatment moderators, and we'll also give some examples. In the presentation, I will have regression models listed, and I'll also have diagrams. And the intent here is to capture different audiences, one a more clinical and more policy-oriented side, and the other is a more statistics and method sides. So just look for whatever is making sense to you on these slides. And again, I've actually had some professional help in putting these things together to try to accommodate both audiences. The papers that this is coming from are reviewed in these two here. And if you want, you can email to me at michael.kashner@va.gov, and I will send these to you. I can do that under the terms of the publisher, but I have to be asked, and so I can't mass distribute this. But I'm prepared to do that. You may already have this. These papers, along with the papers in this journal, were actually sent to all VA researchers about a year ago by the Office of Research and Development, as well as my Office of Academic Affiliations. Again, all these papers come from a special VA issue published by the International Biometrics Society in their issue of biostatistics and epidemiology. You can get this online, and you can see my email address there. And here are some of the other papers that are attached to that. let me just give some parenthetical comments about analytics. We always talk about data and analytics. And when I see the Data Governing Council and their progeny talk about data and analytics, it's about 99% data and 1% analytics. Analytics is really multidiscipline. It includes biostatistics, which is more of a public, and epidemiology, which is more of a public health orientation. These analysis of BAMs are more econometrics done by economists, and there's a slightly different orientation, which I'm hoping to bring this to the attention, at least to your groups. One of the things that I found fascinating is the misunderstanding that leadership often has of our statisticians, and I like this little comic where it says, "Sally, your output is just cutting it. You produced only 15 lines of code." And she says, "Well, you mean the 15 lines of code that cured cancer?" And he says, "Yeah, 15 lines is just not enough. We really need more." The other thing I would want to caution about is what I've often heard among VA leadership is lies, damn lies, and statistics. The quote is attributed to Twain. It actually isn't. It comes from Leonard Courtney, Lord Courtney in England, and the full quote is, "Still, there are some easy figures the simplest must understand and the astutest cannot wriggle out of." And that's what we're trying to do here, is find those easy statistics that the astutest cannot wriggle out of and that people will understand. Let me start by talking about prediction versus explanatory. Predictive models are frequently done, risk models, and their intent is to predict risk. How they get there, it often doesn't matter. Now, people say it does, but the truth of the matter is that the performance of the model is judged strictly by how well it predicts. In 2012, I was asked to give an editorial to talk about expanding observational studies to include more exploratory models, which I did. And here you can see that you've got observed covariates that are affecting both a factor and an outcome. And here we can talk about a choice of pain relief, and we can talk about the health outcome of that. And what you're wanting to do is to look at the association between that choice of pain relief and health outcome. And the problem is that you're going to have covariates that are confounders. And as you can see from the diagram, what a confounder does is that it gives a different pathway for that choice to affect your outcome. And so the point here is to get rid of that pathway so that you can look at an association between choice and outcome independently of all of the confounders. Well, this was done by Blanco, Carlos Blanco, Wall, and their group. And what they discovered is that pain and substance use disorders were associated with each other. And this was a little bit more complicated of an association, because since they were using survey data, you have pain affecting the substance use disorder, and the use of substances was also affecting their pain. So what they did was able to distinguish between that. Now, I was also asked to write an editorial by the American Journal and talk further about what else they could do. And I said, well, let's look at causal modeling. Causal modeling focuses on a cause that occurs before an outcome, and it controls for all of the confounders, not just the ones that are observed, but the unobserved ones. And you're unobserved either because your data doesn't have it, or it's not known, or for some reason you've excluded it from the analysis inadvertently. But you can see from the diagram here that there are many pathways between pain and substance use disorder. And what you're trying to do is to control for both the observed and the unobserved covariates. You're also focusing on moderators. And you all know, I think, what a moderator is. That is something that affects the association between pain and substance use disorder. So for instance, if the person is resilient to having an addiction, then the association between pain and substance use disorder will get a lot smaller. Changes in pain is not going to lead to too much change in the incidence of use disorder. What a randomized controlled trial does is this: if you could randomize patients by pain, of course that would be illegal, but if you could, then what a randomized trial does is that it basically disassociates the pain from both the observed and the unobserved covariates. So you can also think in terms of treatment plan, and it breaks this connection, and therefore you can measure this one brown arrow here, which will be the association that you're looking for. So that's what a randomized controlled trial, and it does it beautifully and perfectly, and that's why we appreciate it. Why do we want a causal model? Well, it's more than just explanatory. We want to look at the change in causal factors that leads to a change in outcome. So if you reduce pain through some policy intervention, we want to know how substance use disorder is going to be reduced. So it's these changes we're trying to predict. Now, to do causal modeling, there are many that are out there. One focuses on the cause, one focuses on outcomes, and another one focuses on both. We're only going to be looking at two today. Propensity scoring, I think most of you already know. This was done by Rubin, very famous. And basically what that is that you eliminate the association between observed covariates and causal factors by doing a matched between your treated and your untreated samples. Again, if you're looking at treatments, and you match it along a propensity score that is supposed to incorporate these observed covariates. The problem is that it really doesn't directly deal with the unobserved covariates. And Rubin and others are saying, well, but these are correlated with these unobserved factors, and that's how we are able to capture them, which is good. And again, just to kind of remind you as to what propensity scoring does, it has a subsample of treated. You divide your sample into those that are treated and untreated. Again, this is an observational database. And then you divide each of these subsamples into categories of propensity scores. And then you measure the outcome of each, and then you subtract by propensity score the treated and the untreated, and then you can take a simple average of that, and that gives you an average effect size, which is what propensity scoring does. The advantage is that you can test it because you can look at your treated and untreated matched samples, and they should also give you equivalent ages and genders and substance use histories and the other factors that you've constructed your propensity model. The most important thing is that it avoids modeling outcome. That's a big deal. Modeling outcome is really difficult. Modeling choice is a little easier, but outcomes are very complicated. And it gives you an average effect size, and you can still do subgroup analysis. Now, there are problems with propensity scoring that these other methods is designed to solve. One, there is no test for unobserved confounders or controlled. They can't test it because you have to measure, you have to be looking at outcomes, not just the causal factors in your modeling. So they can presume this, and it looks good, and everyone likes it because you're using matched designs, and everyone is taught matched sampling and epidemiology. So this is a fairly well accepted and a very persuasive strategy. But you don't measure this. You don't really test for it. The other thing is that you can look at moderators. You could look at subgroup analysis to see how things change, but that's difficult to do. You can't model it. So what we came up with is best approximating models, which is an extension of a control function. What we're basically doing here with control functions and our methods is to attack the association between the observed covariates and the outcomes. In other words, we are modeling outcomes. And the intent here is to break the connection between these confounders and to use other variables in order to pick up the unobserved confounders in order to break this connection. If you break these connections, then there's no other pathway other than the one that we're looking at in order to measure it. Now, what we've done to expand this is that we've made it systematic. We're now testing directly for model misspecification. We want to know if the model that we have, modeling outcomes, is correctly specified. Just to give you an idea of what a BAM is, the first thing is we start off with a covariate pool. Again, we're trying to build a model to predict outcome. We start with those that are plausible. Then we look at a univariate analysis of each of our possible covariates. Most people do a 0.20 here in their significance level. We do a 0.95 and even a 0.99. It has to be deader than doornails, otherwise we will include this as a plausible covariate. Again, we're trying to make sure that we capture it all from our data set. We then do design of these plausible variables, and that means we transform them. If they're in order to look for nonlinear effects, we can recode them, aggregate them, and we can also do interactions. Our experience is that the interactions, 2, 3, and even 4-way, is where a lot of the information lies. It's not the direct effects that tend to matter. We've found that these interactions has lots of information in it, and so we depend on interaction. The next thing is we reduce the design, number of these pools, which could be 40 or 50 or even 60, by using a stochastic search process, which I'm not going to go into very much. But essentially, we reduce that to look at those variables that will plausibly be included in a final model. Then we search exhaustively for models for the final reduced pool. Now, what this means is that we don't do stepwise regression. That's horrible. It's primitive. Don't do it. Only for examination of your data. When you do an exhaustive search, it means you look at every possible model in your model space, and then you look for the best ones among those. We have found that stepwise will not give you the same thing as an exhaustive search, and often it's very, very different. We then do something quite unique, and that is we exclude what we call an unqualified search model, and that is we test for model misspecification. If it tests positive, we get rid of it, and that's one of the things that we've developed. Stephen Henley with his grants, and with Richard Golden and with Hal White. We test for specification, and I'm going to explain that. Then what we do is we validate, as most of you will do, but we use a non-parametric bootstrap. We then rank these models based on essentially the R-square. And we can look at a single model, which is the best one, or we can look at multiple models, basically the top models that we found. And then we can estimate the effect size by looking at the top model, or we can model average all of the other models that are so-called observationally equivalent to the top model. It means they're not statistically different from it. And then we can conduct sensitivity analysis to see how robust our estimates are. So that is what a BAM model does. The advantage is systematic, it's reliable, and it looks over the entire search space. multi-modeling accounts for model uncertainty. So it's not just looking at a sampling error. We can look at whether the models that we're using and how uncertain those models are in order to include that in our confidence interval. Then it also tests, again, for model misspecification. Here's some of the papers we've done. We've gotten 2 reviews. We've got 3 math papers out of this, 4 editorials, 6 applications. One of the applications, interestingly enough, was in a surgery journal, and they put our results on the cover of the journal. So they were obviously impressed with some of the newer techniques. And I can send you these. These are all listed in the paper. Let me talk a little bit about model misspecification. Here we're looking at dose, and increases in dose is likely to of an opioid is likely to cause an increase in the risk of the addiction. Now notice we have these are the actual data points, and I show this as a density, and the true data generating process, that's from God. That is actually what your data is doing. This is a computer that has a random term, and it has dose and dose squared, and it has parameters, and it will actually give you each of these data points. And the ideal model is that the random term and these terms are independent of one another. In other words, they're uncorrelated. Now, let's suppose the researcher has this kind of a model. All right, so it's a straight line. Well, here we've gotten rid of the d squared term, and this is a model that we're using. What does this mean? Well, it means that what we will predict from our researcher's model is going to be less than the actual that will occur in nature, because nature is reflecting the data generating process. So this underestimates risk. Here it's reducing. If you reduce the dose and you're at this part of the curve, then you're going to overstate the reduction in risk. So we get wrong results if we're using the wrong model. Now, how do we know from the researcher's model that it's wrong? Well, if you look at the difference between the points and the researcher's model, it fits a definite pattern. There's a relationship between where you are in dose and whether you're undervaluing or overvaluing the risk based upon your data compared to the researcher's model. So what we do is we look at the correlation here. That is the key to looking at model misspecification. And let me just proceed. So our formal definition is that if the model you use is such that if you plug in the right values, it will give you the true data generating process. So in our example here, if our model would have been d squared, and d cubed, of course, the true data model does not have a data cubed in it. But if our model was this, then we would say this model is correctly specified. Why? Because we could replace the coefficients to the true values of the data generating process, and this one would just be 0. So what we're saying is that if the researcher's model is capable of finding the data generating process from the data that you have, then you say that the researcher's model is correctly specified. Now, let me kind of give you, let me give you some examples of this. Here we were looking at cognitive impairment and medication adherence in an observational study of patients with heart failure. And the true data generating process actually had a square term in it. If we use the simple regression without it, we got the wrong answer. The reason why it goes down and up here is because the family comes and gets involved and helps the patient out. Now, here's an example of having a covariate that we don't include. Notice in this model, we've got dose, we have addiction risk, and we have addiction history. And if this were the true data generating process, and this tells us that as our addiction history increases, our curve rises. It's basically increasing because we're more prone to addiction. And so as we increase both in dose and our background addiction history increases, then our opioid addiction risk will also increase. So what you want to do when you do a causal modeling is to control for all of these other confounding factors. And this is what happens. So if you're looking at a patient at a given addiction history, now you want to look at the change in the dose and the change in the risk, and you can find it here. The problem, of course, comes is suppose that the dose and the history are correlated, and they likely will be, because you're not likely to get a higher dose if you have a high addiction history. What that means is that we're now on this curve here. If we exclude this, this term, and again, how we can know that this model is wrong is because the value and the residual, the error term in the model, are going to be correlated, and that's because it's not picking up this value. Now, the way economists and the econometricians solve this, and the BAM solves it, is that you add additional covariates so that the final model will leave your dose and your residual to be conditionally independent. That takes care of this. These additional variables that you're adding are really designed to pick up this term here. Now, you do that in propensity scoring, but you don't look at it specifically and you don't test for it. That's why testing the actual outcome model will work. I'm going to bypass this section. This is the way we test it. Basically, we test it by looking at a characteristic of a correctly specified model. The two main methods for estimating your covariance matrix, which is your standard errors, is that the Hessian version and this other out of product gradient version will be equal. If they're equal, if the model is correctly specified, they will be equal. If you find that these matrices are not equal, then it cannot be correctly specified, and that's our that's our test. And I threw this in here. It says, before I make my decision, I'd like to see those meaningless statistics again. Now, we do test for the specification. Does this specification test work? So here's the model from God. It has the coefficients, and it has x1 squared into a cubed. And x1 is just a variable that goes from a -1 to a 1. The correct model that we use, of course, is the same, only we're now estimating these coefficients. Here's a logistic regression in which the incorrect researcher's model, instead of having an x1, we have the square root of it. And instead of having an x1 squared, we have a new variable x2 that's just merely covariant. We did a parametric bootstrap of 10,000 samples and the sample size of 1,000 all the way to 16,000. And we tested, did the correct and incorrect model claim to correctly fit the data? And it did. So these two models not only fit the data well, but we cannot distinguish them using the discrepancy risk model selection test. As you can see, they're not distinguishable. So model fit does not work to distinguish these two. However, we can distinguish it with the our specification test. Here, we're wanting to know that if we set the alpha level for rejecting the hypothesis that they're correctly specified, we want to make sure that we get it. So if we specified it at 0.01, we're basically getting it. Some models are a little bit more, tests are more conservative, but for all of these different tests that we have used, we basically are getting at the proper alpha level. So if we specify an alpha of 0.1, that means that in 10% of the cases, our test will claim that the model is misspecified when in fact it is. Now here's the area under the ROC curve. Obviously you want to have it at 1. This looks at both sensitivity and specificity, whether or not you're identifying models that are correctly specified or identifying models that are incorrectly specified. And as you get to a sample size of around 16,000, most of our tests are very, very close to 1. So these do tend to work. Now this is an interesting slide. What we do is we've taken some tests on HIV patients with bone mineral density loss, and we're modeling this. What we find is what we want to be is around here. This is where we have the best fitting model, and we have models that are very close to being correctly specified. Notice the relationship here. As we find, and each one of these points is a model estimate. We estimated 65,000 models, and each model we had an estimate of the fit, and we had an estimate of how close they were to being correctly specified, where 0 is correctly specified and 140 is the best fit. So you want to be in the origin here. So notice something quite interesting. If we look for a model that is that has the best fit, we're most likely we'll find models that are incorrectly specified. So it matters to look both at the fit and the specification, because this is where you want to be. You want to be in the best fitting model and also the one that tests positive for the specification, and that's going to be the ones that you have down here. Does it work? Well, let's look at comparing propensity scoring with this BAM analysis, and we made this up. This is the this is the data generating process for an outcome that's either 0 or 1. You're either addicted or you're not. This is the treatment, pain, opioid-based versus therapy. Then we look at the patient's age, gender, their attitude towards treatment, and education level, and then we make up some of these 7 variables that are random that really don't relate to it, but we throw them into the mix, and then we have the residuals. So here's a logistic regression. The true value is 2. That's what we're trying to find. That's our effect size. It corrects for these variables here. Age, gender, and attitude are all confounders. Why? Because they not only affect outcome, they affect your treatment choice. So older people, males, and those with poor attitudes are going to pick they're going to choose the opioid treatment, and those that are less likely or more likely to choose the therapy. Then we have this attitude, and we assume that attitude is a function of education. So this is an unobserved confounder, and attitude is something that is not in our database. It exists in our data generating process, but we don't see it. So in our simulation, what we do is we say, okay, well, let's take attitude out of the equation. So we make this 0, in which case we do not, the propensity score is based on all of the relevant factors, age and gender, in predicting whether or not you get an opioid therapy or not. And then let's look at a negative effect size and a positive effect size. So as you go here and as you go down here, the attitude as a confounding factor becomes more and more important because it has a bigger effect size on outcome. Now, here's our BAM analysis, and where we lose faith is when we do not throw out a model that we've tested to be misspecified. So if we include those models that are not tested for model misspecification, then we don't predict the true value. Notice the true value is 2. That's what we want across all possible coefficients for this unobserved confounder. 0, of course, means the confounder doesn't work. It's not confounding, and here is where it maximum confounding negative and maximum confounding positive. So what this is saying is that we must test in this particular example, we must test for model misspecification in order to get the right BAM. This is now comparing BAM, fully loaded, testing for model misspecification, and we compare it with the corresponding propensity score. Notice they're all the same. Propensity scores and BAMs will give you the true estimate of 2 if the attitude has no effect on your health outcomes. But as attitude becomes a more important unobserved confounders, propensity scores give you a lower estimate, and it can give you a higher estimate depending upon the relationship between attitude and health outcome. And we've done this with other studies as well. But so what this is suggesting is that if you have unobserved confounders, we need to do it. So it's a little bit perilous when you're not looking for model misspecification, especially when you're focusing on outcome. Now let's look for accounts for moderators. There was a study done by Windhusen in 2010, published in the Journal of Clinical Psychiatry. And what they were looking at was a methylphenidate patch, which was supposed to help patients with ADHD. But in this particular study, they wanted to look at that randomized trial to see if that patch reduced smoking. Okay, so it's a non-opioid alternative to dealing with addictions. Well, they found in this randomized control trial that the placebo, which was a patch that did not have the agent, and the one with the methylphenidate chemical in it, gave you basically the same thing. This was not statistically different. And even though according to this, the patched group did a little better, but it was not statistically significant, as you can see from this. So they basically concluded it didn't matter, it doesn't work, it doesn't hurt, so do it at your own will. Well, the fine folks from the Psychiatric Institute in New York and Columbia University Department of Psychiatry took this data and they did subgroup analysis. But they didn't do a BAM, they did subgroup analysis. And what they did was they divided patients by quartile, fourth, third, second, and first quartile based upon baseline symptoms. And what they found is that the patch reduced smoking, prolonged abstinence, that's what this is. So you want to be high here. So it actually prolonged your abstinence of smoking if you start off with a high degree of baseline severity in the ADHD symptoms. Notice this little fellow here. If you didn't have any symptoms, apparently the patch had a negative effect. In other words, the people with the patch were doing worse than the placebo. Then they looked at, well, let's look at improvement in ADHD symptoms during treatment. And again, they found this little fellow here, these folks here, that only had a modest improvement in their ADHD symptoms. But when they got the patch, they were actually doing worse than the placebo. But in the highest quartile, the ones that had the most reduction in symptoms of ADHD, they were doing a lot better than that. So what these folks did was that they combined the two. So they reduced the sample to include only 50% of the sample in which they had a high level of baseline ADHD symptoms. And then they divided this 50% of the sample that had the high baseline ADHD symptoms into 4 quartiles, looking at the ones in which you have a reduction in symptoms. And so what they found is that this group here, miraculously, with the patch, did a lot better than those without, given that they had high baseline symptoms, and given that the treatment did tend to work in reducing their ADHD symptoms. And so they concluded that the treatment of ADHD with stimulant medication may help nicotine-dependent patients quit smoking, particularly if you have severe symptoms and your ADHD symptoms was also responding to the patch. We did a BAM. This came out in 2015. This article was in 2012. We did include Winhusen, who was the author of the original study out of the University of Cincinnati. And this is the BAM that we did. Here's the patch 01. Here's the patch interacting with lifetime history of substance use, employment, and then the ADHD rating scale that we optimized at a cut point of 36. And what we found is there was no effect. This was statistically insignificant, but it was in the model because we clamped it there, and we did not find any direct effects of the patch on outcomes. But we did find that from these interaction terms, using this systematic approach for finding all of the interactions, that if you did not have a lifetime history of substance use disorder, and you had severe ADHD, and if you were employed, now that was not statistically significant, but it was in the final model that was tested for model misspecification. If you had all of these, then the patch helped you tremendously to sustain your abstinence of smoking for those people in this program. Notice this little set of results. It's harmful if you have a lifetime history of substance use disorder and it's non-severe ADHD and unemployed. In that case, giving the patch is harmful. And you ask a clinician about that, and many of them told us, well, of course, if you have a history of substance abuse, you're unemployed, probably working and walking around people who smoke. Having this patch on gives you the confidence to smoke because it says you're doing something about it. I'm wearing the patch. I'll just go ahead and smoke a little. It's not a big deal. While if you have all of these things, and notice we did not find anything about the effectiveness of the patch on your ADHD symptoms. That was the wrong factor. It was really your lifetime history that was important. Well, let's compare the BAM results, which is telling you, hey, it's harmful. There's side effects here. Worry about this, from the results that were published 3 years before. Oh, just go ahead and do it. It may help. And it doesn't matter. There's no side effects. We didn't find anything. So go ahead and report it. And you might wonder why your patients don't always believe you in terms of about side effects. So we got a lot of backlash from this. And they basically said, well, you're searching for this. Well, this is a systematic approach. And what we're saying is with BAM analysis, you're actually finding a model, just like if you have a model and you're looking for a parameter estimate, you look for an estimate of that parameter. When you look for the estimate, when you estimate a parameter value, you look at all possible values and you pick the one that has the greatest likelihood. This is the same thing with what we're suggesting you do with models. You find the model that will have the best likelihood after testing for misspecification. So that's what we were doing here. And I love the Yogi Berra comment. If I hadn't have believed it, I wouldn't have seen it. So just in conclusion here, model specification is an empirical matter. It cannot be inferred from fit. In fact, your objective of getting the best fitting model is most likely will give you the less likely of having a correctly specified model. So you need to look at both. Drawing inferences from misspecified models can be misleading. Models better fitting the data are more likely to be misspecified, as I said. BAMs are the old-fashioned econometric control functions, but it's based on an exhaustive search. It tests for model misspecification, and we also include a moderator effect size, whereby the effects are going to be assessed not as an average for a sample that we really may not have any knowledge about, but we represent it as an equation. So now we can determine effect sizes and how it might vary depending upon characteristics of the patient. And we found that BAM was, in some of our simulation studies, might be superior to propensity scoring in the presence of uncontrolled, unobserved confounders and in the presence of multiple observable moderator factors. Our suggestion is that you do both. Propensity scoring does have advantages. It is extremely powerful, and we are not saying to replace it. We are saying that you need to do both, and that may cost you more money for your statisticians, but it is well worth it to see and to confirm your results. The biggest problem is BAM software availability, and I'm particularly impressed with this little cartoon. Originally came out in 1920, in the 1920s. This cartoon came out in the Boston Globe, who copied it in the 1940s. And it basically shows a drunk saying to a police officer who says, I'm looking for my quarter, I dropped it here. I'm looking for the quarter I dropped. And he says, well, did you drop it here? And he says, no, I dropped it 2 blocks down the street. And then he says, well, then why are you looking for it here? He said, well, because the light is better here. And for those who may not get the significance of this, the police officer is your patient. The drunk is the researcher. The scientific truth is the quarter he's trying to find. And the light is the statistical software that you're using. This little guy heard this presentation yesterday, and he really liked it. So I hope you like it as well. And I've got 10 minutes for questions, and am willing to do that.
Thank you, Dr. Kashner. That was very informative. That was a lot of information, and I see we do have a question already. I can either invite Stefan to ask his question, or I can read it.
Can you hear me?
Perfect. Yes.
So I'm still absorbing this, and it is possible that I'm sure there's a lot more I need to understand to say this right, but the presentation was about individual understanding associations between a variable or a treatment and individual outcomes. And a lot of my model concerns sometimes get more acute when I see papers published by often economists looking at a variation in a treatment at the county level or at the state level over time, and an association between that and maybe a county or a state level measure. There was a paper a few years back that showed that liberalizing naloxone was associated with increased likelihood of overdose at the county or state level. I can't remember which. There was actually a paper from another group of economists suggesting that the VA opioid safety initiative was associated with suicide. But again, it was modeling at a sort of geographic level. And I'm wondering if BAM is applicable in that kind of situation, and whether the risks of misspecification are the same across studies of individuals as opposed to studies of regions, or if they are different.
Well, that's a very good question. And I will tell you, we really have not studied thoroughly aggregated data. They are problems. All kinds of things can be hidden in aggregated data that we may not be able to disentangle, which is the problem that you're talking about. I can speculate that with aggregated data, you might be able to test for model misspecification, but we really have not looked at that. So I have to confess, I just really don't know. We know we have it. We certainly have seen it, but how these specification tests work with aggregated data, I really just don't know that.
Does that answer your question?
It's not a happy answer. We have run simulations with different kinds of aggregations, and the thing is that aggregation in and of itself is a modeling process, and the correct approach would be to attempt to model the aggregation process in order to arrive at the given result. So you have the model at the individual level, and then you have the model at the aggregation level, and then you're literally trying to test the two models, and that's why this is kind of confusing. We have not done that. Well, we've done a little bit, but it's nothing that we can really report conclusively.
Thank you. So there's another question about whether what software is available to conduct these analyses.
I know of one software, that is the software that Stephen Henley has done. It is remarkably good. He's spent 10 years developing it. He's gotten over $10 million of NIH grants from the SBIR program. It's workable. It's not commercially available, but he has used the software on other people's data file. If you send me an email, michael.kashner@va.gov. Very simple. I don't have any numbers. It's just first name Michael, last name Kashner with a dot, and then va.gov. I can send you his address, and you can talk to him. We do know the Chinese are very interested in this. The math papers that we've sent out have been well cited there, and we know that they're developing. We basically told them, yeah, it works. You can do it. We have software that it'll work. So we know the Chinese are and the Koreans probably have software, but nothing really that's commercially available. Hal White, who founded the original information matrix test, was asked by SAS to come out there and give them advice. He said, well, put a test for misspecification, and SAS basically said no. They didn't see the need for it. By the way, drug companies do not want you to do this. We have contacted several of them, asked if they were interested in it, and they have flatly said no. The reason why is that when you do a randomized controlled trial, you're doing an average effect size, presumably for a population that's amenable to treatment, which is scientifically valid. You want that. If you have a negative finding, you need to be sure that you're doing it on the population that's most likely to succeed. The problem is that they don't do a BAM moderator analysis so that they know which patients are most likely to benefit. Rather, they just report the average effect size, and that blends in better for their marketing purposes. So we haven't really gotten a lot of interest from the pharmaceutical industries for this. But send me an email, and I'll forward that to Stephen Henley, and he also may be able to help you with that.
So two kind of final questions. I see we have only about 3 minutes left. So Ken Taylor, it looks like, has a couple questions here. Rather than specific causal effects, if focused at estimating specific causal effects of a treatment on the outcome, then how does BAM avoid introducing bias introduced from colliders and or unnecessary mediators?
The thing is that the mediators that we don't test for. We can build for that, but we actually don't test for that. So the analysis that we've done basically assumes that the causal factor is directly affecting the outcome.
So I guess to wrap up, I would say if an investigator is interested in learning more about this or potentially using it in their work, what kind of maybe general recommendations might you make to them other than sending you an email and having you send them the papers that you've graciously already offered to share? Is there anything additional that you'd recommend?
Okay, well, let me point this out. When we did this expert panel, and that ended in 2015, 2016, and then we did this special issue. This one, it came out. This was the panel recommendation, and you can get that from Biostatistics and Epidemiology in December 2020 by Taylor and Francis online. What we were suggesting here is that many studies, many principal investigators could probably benefit tremendously if they put more resources into their statistics and their analytics. That would include not only bringing in traditional biostatisticians, but psychometricians, econometricians, and others who have really direct modeling experience. The reason why Windhausen failed in their study is that the statistic is that they just basically did a simple t-test on a randomized controlled trial and they were done with it. There is a lot of information that is contained in many of these databases, but you need statistical power to get to it by people who understand modeling, who understand observational data sets. If you've got a survey data, then you need a psychometrician to perhaps help with those issues. So what we're suggesting in the short term is that you think very creatively with your statistician when you're planning the analytics of these studies, so that you'll get the most out of it. If you take anything away from this lecture, I'm hoping that you take that. Paying a statistician 10–15% time for a $750,000 study where you have lots of complexities in your data even if it's a randomized control trial, seems really lightweight. So that's what I think I would do. Really rely on you're talented, and you don't necessarily have to limit yourself just to one biostatistician. You can bring in some of these specialists to help you.
Thank you, Dr. Kashner. It's 2:01, so I'm going to go ahead and wrap up and say thank you for joining us today. I think I echo everyone saying that we would actually love to have more money to have more biostats expertise on our trials. That would be wonderful if that could happen. But point well taken. And thank you for joining us today. I want to thank everyone else for being here and for your questions. I'm sorry we didn't get to, there are a couple that we didn't get to. Thank you. Enjoy your September, and we will see you next month.
Thank you.
Thanks.